Balancing equations. That's the start of our next unit. Balancing equations is set up for us to demonstrate the law of conservation of mass. Okay, law of conservation just says that nothing can be created or destroyed, right? So whatever goes into a reaction, the same amount has got to come out. It may not look the same because if it's especially like a chemical change, we're going to have something that looks different. Something new is made, but the amount or the total mass has got to equal the amount of mass that went into the reaction. Okay. Now, keep in mind, some of it is hard to justify because we may lose something to the environment, like heat. We might produce heat, so it may seem like we don't end up with as much mass at the end of a reaction as we started with. But if we collected the heat, or if we collected the light or the sound, if something else was formed in the form of energy, then when we still combine it all, it should all add up to the same, right? We're not going to create something out of thin air. We're not going to destroy something to where it just does not exist anymore. So we have balancing equations, right? We've got to get to where we can practice balancing equations. And due to our situation with remote and whatnot, we're not going to go completely in depth. We're just going to learn the basics and get an understanding of chemical equations. Okay, so what we need to at least know, if we don't know, or refresh our minds of from what we've learned before, is the parts of the equation. Okay, so if you remember this, great. If you don't, that's okay too. But we have this equation. Okay, you're gonna have this arrow that's gonna tell you you're going from one side to the other. You're making something. You're producing something with some ingredients, right? And so let's just do a generic example where, say, we have x plus yz, and then on the right side of the arrow, we end up with something like xz plus y. Okay, we've got to remember the parts of the equation. This is our chemical equation. It's going to have formulas. Right now, it's a skeleton equation for the most part because it may or may not be balanced. All right. Word equations are a little different, but we need to make sure that we can identify the parts of the puzzle here. On the left of the arrow, if you remember, they're called the reactants. On the right side are called the products. So we put together our reactants, they react, and the products are produced. Okay. The arrow, more commonly known as yields, okay, otherwise known as produces. So we mix these reactants together, they react, they produce, they yield the products. Okay. In this case, they just sort of rearrange. X is the lone element and YZ is a compound, and they just switch partners. Now X is with the Z, they're a new compound, Y is a lone element. All right. If let's say X was 2 grams and Y was 1 gram and Z was 4 grams, then we're looking at a total of 7 grams, right? 2, 3, 4, 5, 6, 7. We're looking at 7 grams total. Well, on the product side, the X should still be 2 grams. The Z is 4 grams. So this compound right here is 5 grams. This one is 6 grams. Okay. The Y is still a gram. So the 6 plus the 1 is 7. We're still looking at 7 grams. So we've still obeyed the law of conservation, where we started with 7 grams and we ended with 7 grams. We just have things that look differently. Okay. So when we balance equations, we have to show that we are obeying this law of conservation. Now, a couple things we need to know ahead of time. Okay. I don't know that I will give you very many word equations. And when I say word equations, I mean something like, it might look like this. Hydrogen, gas, we'll be a little more specific. Hydrogen gas reacts with oxygen gas to produce liquid water. All right, that's a word equation. We would need to take these words and transcribe them into the chemical equation. Okay, so we would take hydrogen gas, and we would put that like this, and we would have to know, I'm about to show you this in a minute, we would have to know, memorize, and just know that when it says the word hydrogen, it means H2. Now, if it already tells it's a gas, we would have these little symbols, and right now it's not that important. Okay, reacts with, so that means plus oxygen gas. Well, we're going to find out that when it says oxygen, it means O2. It's also a gas, but that's not important right now. And produces, right? That's our produces liquid water. So H2O. In this case, it's in the liquid form. Or a lot of times you see an L like this. Okay. And there we go. That's our skeleton equation, because it may or may not be balanced. All right. So now, let me preface this real quick. It says hydrogen. We have to know and understand that it means H2. It says oxygen. We have to know that it doesn't mean just O. It means O2. Okay, so I'm going to go back up here to the periodic table, and there are something known as diatomic molecules. Okay, diatomic molecules. Di meaning two, right? Atomic, atoms. Molecules means the sharing, the other term for covalent compounds. So we got two atoms sharing, all right? Specifically, two of the same atoms. Two of the same atoms bonded together. They're like twins. Now, there are 7 of them, and you'll just have to get to where you memorize it. They're not difficult to memorize. They're not spread all over the periodic table. They're actually pretty close together. So if you're looking at any periodic table, it's really not going to tell you where they are. It's not going to pinpoint them. You'll just have to know that most of the time you can look at the periodic table and you've got your noble gases, right? This group here, and they're pretty noble, so we just leave them alone. So we look at this periodic table now right here, like this is our border. Here's this corner, okay? This corner is the top corner edge of where our diatomic molecules are. I'm going to border these right here. All right. So N and O and F and Cl and Br and I. That's 1, 2, 3, 4, 5, 6, but there should be 7. Okay, this even looks like a 7 right here. Well, the 7th one is over here on the far left. That's hydrogen. All right, hydrogen is the 7th one way over here. It naturally occurs in the environment also as a diatomic molecule, meaning it's paired up with its twin, H2. All right, so if you see the word nitrogen or fluorine or bromine, iodine, oxygen, chlorine, hydrogen, they're paired up with their twin. All right, they're diatomic. So they're going to be 2 of them. So you can think of it as like an acronym. This is what I always like to tell my students. It's usually, you've got these things in life you just need to be careful of or be aware of. This is one of them. Okay, never offer freaky clowns breakfast in hammocks. You should stay away from freaky clowns anyways, let alone offer them breakfast, and more importantly, don't offer them breakfast while in hammock. All right, so never offer freaky clowns breakfast in hammocks. maybe that'll help you remember the nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen are your diatomic molecules. They're going to be bonded or paired up with two of them. It's not just going to be a singular F unless it's already spelled out for you in a chemical equation. Okay, so we've got those. Okay, not difficult to memorize. So now let's get into balancing equations. I have this example right here. We had our word equation. Then we go to our chemical equation. It's also known as a skeleton equation because it's not balanced. And we reference a few things. Okay, so don't worry about the phase of matter. I'm going to delete it right here. What we need to note are the subscripts, right? There's 2 right here, hydrogen, 2 right here, there's a 2 right here. We cannot change those. Those are set. That's what makes those molecules or compounds or elements what they are. Okay, they're either there or they're not there. Meaning we can't when we go to balance this, I can't just put a 3 right here to try to balance something out. Okay, I can't just take the 2 off of here to try to balance things out. If I change those things, then now I no longer have water. I'm with something totally different. Okay, so when we go to balance, if you've done this before, you might remember. If not, that's fine. We can add what are called coefficients. Okay, the numbers out front, right? Right now, they're all understood to just have ones, which we don't have to write the ones, but it's understood to be ones. So the coefficients, it just represents what's called a mole. Okay, English language likes to use words for a lot of things, right? So mole, you might think something on your back or something in your yard, but really in chemistry, it means the amount of substance. Okay, there's a little bit more to it, but think of it as just the amount of substance. So if I have a 2 right here, that means I have 2 moles of hydrogen. I have 2 amounts of hydrogen. If I had a 4 here, I'd have 4 moles of oxygen or 4 amounts of oxygen. Okay, me, myself, Mr. Christofferson could represent 1 mole. There's just 1 amount of me, and in that 1 amount of me, I am so many grams, if we think of it that way. Okay, well, we can add coefficients to help balance things. So I like to think of it as scoops. If I put a 6 right here, that means I'm putting 6 scoops of hydrogen into the pot. And then I put a 2 here, so then I'm putting in 2 scoops of oxygen. And then maybe I end up with the number here like a 7, which isn't going to happen in this case, but that would mean I'm producing 7 moles of water or maybe 7 scoops of water. Okay, so here's the easy thing. Okay, we've got to have the same number on the left of the arrow as we do on the right of the arrow in order to obey the law of conservation. So for you chart writers, okay, we're looking, here's our dividing line right here, the arrow, right? So on the left of the arrow, my hydrogen count is 2, right? I've got 2 of them. My oxygen count is 2, okay? On the right side of the arrow, my hydrogen count is 2, so I've got 2 right there. So that's good. My oxygen count is understood to just be 1. So are we balanced? Am I starting with the same amount that I'm ending with? Or am I ending with the same amount that I'm starting with? Well, I've got 2 hydrogens and 2 hydrogens. I'm balanced. I've got 2 oxygens and I have 1 oxygen. Okay, I'm not balanced. Somehow I added hydrogen and oxygen and produced water and I lost an oxygen. Where in the world did it go? Well, it didn't really go anywhere. It's just we're not really showing the full picture. Okay, so if I put in 1 mole of hydrogen and 1 mole of oxygen, this really is reaction's not really going to run. It's not really going to produce any water. Okay, I don't really have the full amount of ingredients in order to run this experiment. So we've got to figure out if I have 2 oxygens on the left, then I at least need to match up 2 oxygens on the right. Or maybe I need to go even more and make it like 6 oxygens on the left and 6 oxygens on the right. Okay. Well, we were going to add coefficients, and whatever's connected to the coefficient is affected by that number. Okay. If I put a 3 here, then I've got 3 H2s. H2, H2, H2. Right? I've got 3 moles of it, 3 amounts of it, so that's 2, 4, 6. Or 3 times 2 is 6. So I would really have 6 H's. Okay, If it's a compound, like over here, if this were a 4, that means I've got 4 waters. H2O, 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 H2O. So 4 times 2 is 8, which is 2, 4, 6, 8. There's 8 of them. And 4 times 1 is 4. 1, 2, 3, 4 O's. All right, it affects the whole thing. All right, so now let's go ahead, and I've drawn this out enough. Let's go ahead and balance this, okay? So here we go. 2 H's on the left, 2 H's on the right. They're great. 2 O's on the left and 1 O on the right. It looks like it'd be pretty easy to just say, let's say 2 O's on the left, and let's try to make 2 O's on the right. Well, if I have 1 already, can I get 2? Like 1 times what would be 2? A 2, correct? So I'm going to put a 2 right here. I'm not going to put a 2 right here because then now I'm no longer water. H2O2 is not water. That's hydrogen peroxide. Completely different, right? Okay, so I put a 2 here. That means everything after that 2 is multiplied by that number. It's doubled. 2 times 2 H's and 2 times 1 O, right? Because now I've got 2 waters, H2O, H2O. All right, so what does that mean? Well, putting the 2 there means I've doubled my H's to 4. So now I have 4 H's. And I've doubled my O's from 1 to 2. So I really have 2 O's. So let's go back to the left. How many H's do I have? I have 2. But I just made 4 on the right. Can I make 4 on the left? Yes, I can put a 2 here. All right? It just means I have to bring in 2 molecules of hydrogen. 2, 4. 2 times 2 is 4. All right, so that has 4. So now they're balanced. And then I have 2 oxygens already on the left. And I made 2 oxygens on the right. So now we're balanced. You don't have to write a 1 here unless it just makes you feel good about it. So now, when you think you're done, just double check real quick. I know we've already done it, but 2 times 2 is 4 H's. 2 times 2 is 4 H's. They're balanced. 2 O's. 2 times 1 is 2 O's. All right, so now we're balanced. Okay. If I had something that looked a little less sloppy, it'd be 2H2 plus O2 produces 2H2O. All right. So we could say this is a 2, 1, 2 balanced equation. So in order to even produce water at all, I've got to put in 2 moles of hydrogen, 1 mole of oxygen, and it will produce 2 moles of water, whether I want that much or not. That's what I've got to have to at least initially get my reaction to go. Okay. So let's consider this example, problem number 1. Because with balancing equations, it just comes down to practicing. Okay, because there's a lot of different scenarios, a lot of little tricks, a lot of little bumps, a lot of little trial and error for some. Okay, for some there's a lot of erasing or a lot of scribbling. If we were in class, we would go over a bunch. I'd call on you, and we'd kind of work through it together. And we'd see some easy ones, and we'd see some that are just flat out challenging. Okay, but today I'm going to work 1, 2, 3, 4, 5, 6, 7, 8 of them. All right, to kind of give you some different looks. Okay, so that's example number 1. Let's try example number 2. All right, let's say I've got iron, and I'm going to add it to oxygen, which is O2, and it's going to produce iron 3 oxide, which is Fe2O3. All right. So by rule of thumb, I like to try to teach everyone to start your balancing off, if you can, generically speaking, balancing your hydrogens and your oxygens last, if possible, because hydrogens and oxygens will give us the most challenges. Okay. And then sometimes it doesn't even apply, but usually try to do them last. Okay. In this case, it might help, it might not. I see that I have on the left side of the arrow, if you're doing your little chart system, which you don't have to, I've got 1 iron and I have 2 oxygens. On the right side, I have 2 irons and I have 3 oxygens. So nobody's balanced. Well, I can start with my irons because I like to do oxygens and hydrogens last. So if I have two on the right, two ions on the right, can I get two ions on the left? Yes, I could put a 2 right here. So now I have two ions. All right, and then now I've balanced them. So let's just double check everything. Two irons, two irons. Now I have two oxygens and three oxygens. All right, so this is a case where I'm going to end up having to erase some things because the iron didn't help me out any. I'm going to have to balance my oxygens. Well, I have two on the left and three on the right. I can't put a number here to make this 3 a 2. And I can't put a number here to make this 2 a 3. So I'm going to have to find the next common factor that they can both meet up at, the 2 and the 3. Which, if you've been in math long enough, you probably already know 2 and 3 can both go into 6, right? It's the next greatest number. All right, so that's easy. So 2 times what is 6? That's a 3. So then I come over to the right of the arrow. What times 3 is 6? Well, that's a 2. Okay, so now my oxygens are balanced. 3 times 2 is 6. So now I've got 6 oxygens. 2 times 3 is 6. So now I have 6 oxygens. But when I put this 2 here, it also affected the iron, right? Because it affects everybody right after it. So Fe2O3, I just made 2 of those. So that's where I got my 6 oxygens. But 2 times 2 is 4 irons. So now I just made 4 irons. Well, let's go back to the left. Okay, I made 2 because there was already 1. So I can make 4 just as easy, right? Put a 4 right there. So now I have 4 irons. All right, now I believe we're balanced. I have 4 irons with 4 irons, 6 oxygens, 6 oxygens. That's a 4-3-2 on my balance equation. Okay, so there's another example where we might go one direction and it didn't quite work right off the bat, right? I started with my iron. It didn't help me out. I ended up having to go back and change my iron equation in order to balance it. That's what happens sometimes. Either way, it's not the end of the world, hopefully. Okay, but we're balanced. I got 4 irons on the left, 4 on the right, 6 oxygens on the left, 6 on the right. Now we're balanced. We've obeyed the law of conservation. In this experiment, this equation would actually go and run its course. Okay. All right, let's try the third one. Let's look at just a little longer equation. Let's try AU2S3. And we're going to add that to hydrogen, which is H2 because it's diatomic. It's going to end up producing Au, the gold by itself, plus H2S. All right. So now, let's just see if we're already balanced. Some equations are already balanced. Au, I have 2. Sulfur, I have 3. Hydrogen, I have 2. On the right side, Au, I have 1. Sulfur, I have 1. Hydrogen, I have 2. Okay, so only hydrogen is the one that is not balanced. Is balanced, sorry. Well, my teacher says do hydrogens and oxygens last. Wouldn't matter anyways because hydrogen's already balanced. So let's just pick somebody. When it's that type, I just start at the left and work my way to the right. So I start on the left. It says I have two AUs, 2 golds, and on the right I only have 1. So can I make 2? Yes, let's just bring in a 2. So now I have 2. Well, my chain reaction stopped right away. So let's go back to the left. S sulfur says I have 3. On the right, I have 1. So can I make 3? Yes, I can put a 3 there. That'll make 3 S's. But then I just affected my hydrogens. I had 2. Now I have 6. 2, 4, 6. 3 times 2 is 6. Well, can I get 6 hydrogens over here? Yeah, just by putting that 3 right there. All right. Okay, now it looks like I'm finished. I've got 2 AUs. So I double check everything real quick. I've got 2 AUs and I have 2 AUs. So we're balanced. I have 3 S's and I have my 3 S's. So I'm balanced. I have 6 H's and I have my 6 H's. So I am balanced. All right. There we go. 1, 3, 2, 3. So I'm going to have to put in 1 scoop of this and 3 scoops of this. And what I end up producing are 2 scoops of this and 3 scoops of that. Or you may, when you guys get older and you become scientists and you want to figure out what's it take to produce 4 scoops of this and 6 scoops of this, well, you can figure that out just by balancing it. And you'll realize that, you know what, I'm going to have to put in 6 scoops of this and I'm going to have to put in 2 scoops of that. Just because I'm trying to balance it. All right. Okay, let's go to number 4. I don't remember how many I said I would do, but I'll do as many as I have set up. Number 4. All right. Let's look at this one. Something we haven't seen in a while. Osmium, OS, and then O4. We're going to add that to PtCl4. And we're going to produce PtO2. And we're also going to produce OSCl8. All right, that's a good sized chemical equation right there. Okay, let's just see if we're balanced. I got 1 OS on the left, 1 on the right. Looks good. I've got 4 O's on the left, and I have 2 on the right, so it's not balanced. I've got 1 PT, that's balanced. 4 chlorines, 8 chlorines, not balanced. Okay, so my chlorines and my oxygens are definitely not balanced. I usually try to do oxygens last, so let's try the chlorines first. I have 8 on the right, I have 4 on the left. So let's just even it up at 8. 8 on the right, 8 on the left. So 4 times what? 4 times 2 would be 8. So I got to put a 2 there because 2 times 4 is 8. But now I just made 2 PTs. So I got 2 PTs on the left. On the right, I only have 1. Well, let's put a 2 right here. That'll give me 2 PTs. So now I have 2 PTs on the right to match the 2 PTs on the left. But now I just doubled my 2 O's that I already had. So 2 times 2 is 4 O's. So 4 O's on the right. How many on the left? 4. Okay. That means my chain reaction has stopped for the moment. So let's just double check some things. I still have 1 OS and 1 OS. I have 4 oxygens. And I made 4 oxygens, doubling my compound. I made 2 PTs. And I made 2 PTs, so they're balanced. I've got 2 times 4, 8 chlorines, and I already had 8 chlorines. All right, so there we go. So that's a 1, 2, 2, 1 as far as coefficients go, and my equation is balanced. Now I know what I'm going to need to run this reaction. All right, easy enough. Sometimes they're pretty simple. Let's look at number 5. I'm on my way to number 8. All right, let's look at something with a diatomic molecule. Let's go Fe plus H2SO4 produces Fe2, and then in parentheses SO4, and 3 on the outside, plus H2. All right. Okay, so hopefully you've noticed this one's a polyatomic ion. I've got 3 or more right here. So two of them have got to be acting together as one. Let's switch back to my pen. And we got 1, 2, 3 things together. So two of them are acting together. And I already know that because this one's in parentheses. SO4 is a polyatomic ion, sulfate, and there's 3 of them. So we've got to put it in parentheses so we don't mess up the formula. Well, if you ever come across a chemical equation that you're trying to balance and you see that one of them is in parentheses and you identify it, in this case as SO4, go to the other side and see if there's an SO4. If there is, great. Now we can compare SO4 to SO4. All right. Now this could have been an SO3, like a sulfite, instead of a sulfate. If that were the case, we can't do this. But luckily that's not the case. Okay, we have an SO4, we have an SO4, so let's compare SO4s. Meaning let's not break this up and say, oh, I've got one S and I have 4 O's. And over here, since this is tripled, I would have 3 S's, and 3 times 4 is 12 O's. Now I'm comparing 1 S to 3 S's and 4 O's to 12 O's. Let's not break it up and balance it when I can just keep it together and balance it as a whole. Let's take this big watermelon and compare it to this big watermelon. Does that make sense? We don't need to make any extra work when we don't have to. So I see it in parentheses, SO4. I see there's an SO4 on the left. That's also where I suggest you begin your balancing. Okay, I already know it's not balanced because this one has 3 SO4s. This one only has 1. So right now I'm not even concerned with the other ones because I know this one's not balanced and I know my teacher said start there. Okay, easy enough. If I have 3 SO4s, SO4, 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 I've got 3 of them because that's at 3 right there, then I need 3 on the left. And right now I only have 1. It's kind of like it's in parentheses, but there's just 1 of them. Okay, well, we can make 3, correct? Because I can put a 3 here. That'll give me SO4, SO4, SO4. That'll give me 3 SO4s. So that's good. Now I just affected my hydrogens. I had 2, and I just tripled it. So 3 times 2 is 6. On the right-hand side, I have 2 hydrogens. Can I get 6? Yeah, kind of the same way I did on the left. Put a 3 there. 3 times 2 is 6. All right. Now my chain reaction stopped for the moment. So let's just see if everybody's balanced. I've got 6 H's that I made here and 6 H's that I made there. Check. I've got my 3 SO4s. I made 3 SO4s, so they're balanced. I've got 2 irons, and over here I have 1 iron. That's okay. This iron's by itself. So if I've got 2 on the right, can I make 2 on the left? Yeah, just put a 2 right there. There we go. Now we're balanced. I've got to put in 2 moles of iron and 3 moles of this, and it will produce 1 mole of this and 3 moles of that. But at least I'm balanced now. I'm obeying the law of conservation of mass. All right, easy enough. So if you see something in parentheses, or it may not even be in parentheses, see if there's something on the other side that matches. If it does, then just compare the whole thing to the whole thing. Don't split it up and make it more difficult. Okay. All right, that's number 5. Let's try number 6. Number 6. Let's look at one sort of similar, but not. So say we have Mg, and then in parentheses OH 2 times plus HCl, which is a little hydrochloric acid, producing Mg, Cl2, and H2O. All right. Well, right off the bat, my keen observation skills here shows me that I've got something in parentheses, OH. That's a hydroxide, polyatomic ion. So I'm going to look to see if I have an OH on the right. I do not have an OH here. Nope. Over here, I have 2 H's and an O. So I do have H's and O's, but I don't have an OH. Like I need to compare an OH to an OH. I don't have that. So I'm not going to be able to just keep this as OH. I'm going to have to split it up into oxygens and hydrogens. Okay, so let's just go ahead and do that for the chart, people. On the left, magnesium, I have 1. On the right, magnesium, I just have 1. On the left, oxygen. Well, I've got OH inside parentheses with the 2, so that means I've got 2 OHs. Right? 2 times 1 is 2. 2 times 1 of those is 2. So for oxygen, I have 2. On the right-hand side, oxygen, I just have 1. Okay. Hydrogen on the left. Well, I've got these 2 right here because of my 2 H's. So H's, I have 2 right there, and then I have 1 right here. I've got to add. So I've got 2 plus 1. I've got 3 H's, which is an odd number. It's usually not good to have an odd number. Okay, well, on the right side, I have 2 H's. Okay, last thing, chlorine. On the left, I have 1. On the right, I have 2. Fantastic, fantastic. My H's are split up over here, so I've got to remember to add those together. My magnesiums are already balanced, but my oxygens and H's aren't. My teacher says try to do hydrogen and oxygen last, but my magnesiums are already balanced. Chlorine is not balanced. 1 chlorine to 2 chlorines. Oh, good. So I've got 2 on the right and 1 on the left. Can I make 2 on the left? Sure. Put 2 there. That'll make 2 chlorines. All right, so change this to a 2. Now they're balanced. But putting this 2 here just affected this H. So now right there I have 2 H's. And right here I have 2 H's. That brings my total to 4. So 4 H's now. On the right hand side I have 2. Can I get 4? Yeah, I can put a 2 there. 2 times 2 is 4. So there's a 4. And now I just affected my O's. I just doubled my O's. So now instead of 1 I have a 2. Well, on the left, how many O's do I have? I have 2 because of that parenthesis right there. Okay, so then my chain reaction stops and I double check. 1 magnesium to 1 magnesium, 2 O's, 2 O's, 4 H's to 4 H's, 2 chlorines to 2 chlorines. All right, so I've got a 1, 2, 1, 2 coefficient set up for this. And we're balanced. We started with this many, we ended with that many. It's the same number. We just made different compounds. All right, let's look at the 7th one. We're going to do 8. I just picked 7. I picked 8. There's number 7. Let's look at something that just looks like a lot. Let's go C10, H16. Oh my goodness. Plus Cl. Now, chlorine, if you remember, is diatomic. But in this case, it is specifically already telling us that it's just a Cl. Okay, which usually is not stable because in nature it readily exists as a diatomic molecule. But here, it's just a Cl. So we're not going to change it because that's what it's given us. All right, it's going to produce carbon by itself and some HCl. Okay. Whew. I've got 10 carbons and 16 H's on the left. All right. 10 carbons versus 1 carbon. 16 H's versus 1 H. 1 chlorine, 1 chlorine. All right, this looks like it's going to be very easy. Everybody else is just 1 coefficient so far. All right, so if I have 10 carbons on the left, can I get 10 carbons on the right? Yeah, let's put a 10 right there. I've got 16 H's on the left. Can I get 16 on the right? Yep, just put a 16 right there. 16 times 1. Now I also just affected my chlorines, though. I just made 16 chlorines. I have 1 here. Can I get 16? Yeah, just put a 16. All right, chain reaction stopped. So we just double check everything. 10 carbons. 10 carbons. 16 H's, I made 16 H's. 16 chlorines, I made 16 chlorines. All right, we're good. We're balanced. Looked like some big numbers, but it was easy. All right, let's look at number 8, and then we'll be finished for now. Number 8. This is one that you will see every once in a while, and sometimes will stump you until you remember what type of reaction this is. Okay, so we've got C2H6 reacting with oxygen, and it's going to produce some water and some carbon dioxide. Now, next week we're going to learn about reaction types. Okay, reactions. There are specific reactions. They have names to them to identify. This is a combustion reaction. So all those of you out there that just love combustion, okay, it happens every time you drive a vehicle. Hopefully, just in a safe way, you're combusting stuff. Things are blowing up at a small level. Okay, otherwise it could be a huge level. But if it's combustion, you're gonna, the little red flags are, you're gonna have oxygen by itself. It's gonna react with the carbon hydrogen compound, and it's gonna produce some water, usually in a small amount of vapor, and carbon dioxide gas. Okay, well, there's a little trick to these. They're usually really easy, and then every once in a while you're gonna find the one that just seems like it's gonna stump you, but you're gonna remember the little trick. Okay, so here's what we've got. I've got 2 carbons on the left and only 1 on the right, so they're not balanced. 6 H's versus 2, they're not balanced. 2 oxygens versus 1 and 2, so we've got 3 oxygens on the right compared to 2 on the left. Well, I say do hydrogen and oxygen last, so let's go carbon. We got 2 on the left and 1 on the right, so I'm going to put a 2 here. That gives me 2 carbons. Now that just affected my oxygens, where I had 2, but now it's doubled. 2 times 2 is 4. So now I've got 4 here and 1 here. That's going to give me 5. All right. So my chain reaction stopped, but I know if I come back over here where I didn't mess with this carbon, I didn't mess with this hydrogen, so I've got 6 of them. Over here I have 2. 2 times 3 is 6. So now I've got 6 hydrogens. But now it just affected this oxygen. It gives me 3. So now I have 3 oxygens, 3 and 4. That gives me 7 total oxygens. Okay, well 7 divided by 2 is what? Yeah, 3.5. We can't do that. We can't have half elements. So this one's not balanced. Okay, well, it's a combustion reaction. And every once in a while, when you go to balance a combustion reaction, you're going to have everybody balanced but the oxygens. And then you're going to be like, oh, yeah, there's a really simple trick to this. My teacher taught me. If everybody is balanced, and you know everybody is balanced, then all we need to do to really balance the oxygens correctly is we just need to double everything. Yeah, it's that easy. So let me rewrite this here. C2H6 plus the O2 produces the water and the carbon dioxide. And my teacher said just double everything. Well, okay. Let's see how that goes. Up here, I haven't understood 1, correct? So I'm going to double that to a 2. Put a 2 there. If this were a 3.5, we can't do that. But if it were, I'd have to double it. So 3.5 times 2 is 7. So I'm going to put a 7 right there. Here I have a 3. So I'm going to double that to 6. And here I have a 2. So I'm going to double that to 4. So sometimes it's okay to double things. Now, sometimes you'll double things and you'll realize you really didn't need to. And I'm gonna go off tangent here for just a second. Okay, what I mean by that is, let's say this were, just for fun, say this were a 4, this were a 6, and this were a 4, and this were a 2. Okay, well, those are all divisible by the same number. Okay, that means it can be reduced, right? They all can be divisible by 2. So really, we would want this to be a 2, and this to be a 3, and this to be a 2, and this would just be a 1. And we would reduce it down. Okay, that's what we want to do in balancing equations if we have these big numbers and they can be reduced. Now, I just doubled everything, but I know they can't reduce because I've got a 7 in there. And that 7 is not divisible by anything that everybody else is divisible by. So let's just see if we're balanced now. 2 times 2 is 4 carbons. And over here I have 4 carbons. Okay. 2 times 6 is 12 H's. And 6 times 2 is 12 H's. Good. Here, 7 times 2 is 14 oxygens. Over here, I've got 2 sets of oxygens. I've got this one that's 6 times 1. So that's 6 oxygens. Then I'm going to add it to the 4 times 2. That's 8 oxygens. Well, 6 plus 8 is 14. So yes, 14 and 14 is balanced out. And there we go. We got a balanced equation. All right, so some of this is just trial and error. You just pick something and start going. If you mess up, it's okay. Erase it. All right, but I try to show you a few that might just little tips. Like this one is combustion. It doesn't always do this. A lot of times the combustion reaction just balances out like normal. But if you balance it and you're in trouble because you can't get this O on the left, well, then you probably just need to double it. Okay. Here, you got these big numbers, C10H16. Don't be afraid. That one was easy to balance. All right. This one, it looked like we had a polyatomic ion on the left, but we didn't have an OH on the right. So we actually have to split it up and compare. So just be aware of that. This one, we did have a polyatomic, SO4 on the right, and we did on the left. So compare SO4 to SO4. Don't compare S to S or O to O, because you might end up having to add them to other O's. Number 4, let's just pick one and balance. Number 3, pretty much pick one and balance. Number 2, smaller equation. We went one direction and we didn't have to erase anything, but we started with iron, and we started with iron and found out putting a 2 over here on the left wasn't going to do it because our oxygens needed to be bumped up. Okay, that happens. This one was a classic. We just pick one and see what happens. Okay, so there's your balancing equations. All right. Practice the sheet. It's a 2-sided worksheet. I've got a random answer bank on them, and hopefully I didn't type them too quick to where the incorrectly typed one, but I put a bank at the bottom of the front page and a bank at the bottom of the second page. So as you fill in your answers, you can mark them off. Okay. Now, in real equations, you're not going to see a 1 put in front of as a coefficient, but you can if you want to on the worksheet. If you feel better about a space occupied on the answer bank, you'll see stuff like 2, 1, 1, 3 or something. That's just so you know that those are ones, but they could be blanks. All right. It's not that big a deal to me on this. All right. So if you have any questions, let me know. All right. Good luck.